Hello, lazy chemists, and welcome to today's lecture where we are going to be going over a concept that's called bond enthalpy. And bond enthalpy is essentially a more labor-intensive pathway that we could use to go ahead and figure out how much energy is released in a reaction. And we can do this because we have went ahead and figured out the average amount of energy for certain amounts of bonds. And so because we've figured out that average amount of energy in those bonds, what we're able to do is we're able to kind of see what a compound is, see what its Lewis structure is, and then we imagine what happens when we break all of those bonds and then make something new which forms all of those bonds. So that's our general process for solving problems using bond enthalpy. In my particular opinion, this ends up being a little bit more labor intensive because you have to end up drawing the Lewis structures, and it's also going to have a little bit of nuance errors to it. So as I said before, this is where we go ahead and calculate like the average bond energy for a particular bond. So for instance, if it's a carbon-carbon bond, we say it has, so many kilojoules per energy per mole. But not every single carbon-carbon bond is going to end up having the same amount of energy. So we're going to go ahead and start here. Bond energy is going to be the amount of energy that's required to break apart a bond. Okay, so this is, in order to break a bond, we have to input energy. And then the second part of it is that bond energy is also the amount of energy that is released when a bond is formed. So we're going to use these two interchangeably. So it takes as much energy going into a bond to break it as it does when a bond is released. So the amount of energy that's released is the same amount that would have gone into breaking that particular bond. And one of the laws that goes into how exactly strong a bond is, or that gives us the equation for how to figure out the energy that's within a bond, is a concept that's known as Coulombs Law. Okay? And Coulombs Law defines the amount of energy between 2 point charges. Okay? And in this case, we're going to use point charges as different atoms. Okay? So different atoms are going to have a different partial charges based off of, how well they are distributing electrons around their outer shells. And so that's what we're going to use for what's known as Q1 and Q2. So if you want to imagine that here is one atom and it's bonding with another atom, okay? The amount of charge on atom 1 and atom 2 are going to add to the amount of energy that's in the bond. And then how far away from each other is also going to be an important factor of how much energy is in there. And we have a way of actually calculating this here, where we say, like, the force or the energy equals K, and in this case, K is going to end up being some constant, times the charge of Q1 times the charge of Q2, and both of these end up being absolute value, so whatever the charges are multiplied together, and then that's all going to be divided by the radius squared. And there's a couple of factors that I want you to keep in mind. We're not actually going to be doing a lot of calculations that involve this Coulombs Law equation, but we need to be able to approximate based off of the large conceptual issue around it. In particular, that as the charge goes up, Okay, so as the amount of available charge goes up, the energy of the bond should go up. Okay? And that should make sense. This is something that we're multiplying by, so therefore when it goes up, the charge is going to go up. The second thing that we should keep in mind is that when radius goes down, so as our radius gets smaller and smaller between these two molecules, then the total amount of energy that is within that bond is also going to increase. Okay? Because we divide out r here and we divide out r squared. So that means that radius is a really big driver for how strong a bond is going to be. So this is just something to keep in mind, and an idea for questions on this are going to be, hey, what happens to the energy of a bond when we increase the charge on atom 1? And we should say, oh, it should have an increase. And then we could say, oh, what happens when we decrease the radius? And we should say, hey, when we decrease the radius, we should see a large magnitude of increase, okay? So that, if we decrease the radius, it's a large magnitude change in the energy of a bond because the radius is so much more important to that bond size right there. Okay, and this image is just one that I'm probably going to want you to go ahead and copy down into your notebook. This is a basic idea of how it works. Remember, force, atom 1, atom 2, and radius squared. And this second image here is another thing for us to go ahead and keep in mind. And what we have here is we have essentially hydrogen atoms coming together. And what happens is that the total normal amount of energy for the hydrogen atoms when they're by themselves is fairly high. Okay? And this right here is potential energy, and this is the radius between them. So when the hydrogen atoms are far apart, they have a relatively high energy. But when they come together and bond and they share, they end up releasing their energy. And they release quite a lot of energy. And this releasing of energy is their most stable state. So this is why some things like hydrogen or oxygen or fluorine are always bonded together, and that's because when these atoms are bonded together and they're sharing that last electron or that last pair of electrons that they need to in order to fulfill their octet rule, that those atoms are actually in their lowest energy state. Now, what I also want you to know is that when we push them past this, so if we try and push the hydrogen atoms closer and closer together, what's going to happen is that their potential energy is going to increase dramatically, okay? And that's because there's, once we've gotten past this stable state, we're actually trying to push the nucleuses further and further closer together, which ends up creating, an increased amount of energy until eventually, if we get it close enough, then we'll end up getting to a point of fusion, which would end up releasing even more energy, and that comes from, the destruction of matter and turning it into pure energy from that point. Okay, so that's our basic definition here. Okay, now how do we calculate it? Okay. So we're going to have a total of 4 steps. And I guess we should technically have a total of 5, but like the 5th step is always just going to be to do like the math. Okay, and what we're going to do is we're going to determine the types of bonds broken. We're going to determine the types of bonds formed. We're going to determine how many of each type of bond there are. And then we're going to add the enthalpy change of the bonds broken plus the enthalpy change of the bonds formed. Okay. So bonds broken, that's always going to be a positive value because those bonds being broken have to absorb energy in there. And our bonds formed, that value is always going to be a negative value. Okay. And the reason that it's going to be a negative value is because when bonds form, okay, they end up releasing energy. Okay. So, as a example here, this is another way of kind of showing what's going to happen here, where we're talking about, the total delta H for the reaction is going to be the summation of all of the delta H of the bonds breaking plus the summation of all the change in enthalpy of the bonds forming. Okay, so for right now, it looks like, hey, we're adding bonds breaking plus bonds forming. But this is the same as saying, like, oh, okay, all the bonds of the reactants minus all of the bonds of the products. Okay, and the reason that we're going to say minus all the bonds of the products is because when the products form, they release that energy back out. Whereas the reactants, that's a positive because you have to add energy to break the reactants apart. Okay, so endothermic bonds breaking, basically going for, it's basically saying, hey, we're going to this intermediate state where everything's separated. And then exothermic, the bonds are being made. Okay, so this is another good diagram. This one here is an example of the first one is an exothermic process. This second one is an endothermic process. Notice that the total line ends up being above the initial reactant line. Okay. And now let's go ahead and look at an example. And we're going to look at one of your favorite examples, and I'm going to say it's your favorite because the worksheet that we had, this particular problem, nearly everyone disliked this problem. That being said, I still think it's a good problem. All right, and this says that we're going to go ahead and take C2H4 gas. We're going to add H2 to it, and we're going to get C2H6, and that also is going to be a gas, all right? And then we're going to be like, all right, what is the molar enthalpy for this reaction? Okay, so we're first going to take a look at the types of bonds, okay? Now, this is our first molecule. This is C2H4, and what we should notice is that we have CH bonds, so we have bonds between a carbon and a hydrogen. We have a carbon-carbon double bond, and we have, even more carbon-hydrogen bonds. We also have, from our original equation, we have NH-H bond. Okay? And finally, in our last one, we have carbon-hydrogen bonds. We have a lot of those. And then we have a carbon-carbon bond. Okay? Then we're going to go ahead and add up how many types of each bond that there are. Okay? So here we have a total of 4 carbon-hydrogen bonds, 1 carbon-carbon double bond, 1 hydrogen-hydrogen bond, 6 carbon-hydrogen bonds over here, and 1 carbon-carbon bond here. All right, so that's how we calculate how many types of bonds and how many types of each one. Then what we're going to do is we're going to go ahead and set it up in a formula, and we're going to be like, hey, we have 4 carbon-hydrogen bonds, okay? Well, carbon-hydrogen bonds are 413 kilojoules per mole. So we're going to go ahead and put that, instead of carbon-hydrogen, we're going to put the 413. We have 1 carbon-carbon double bond. Okay, so that's 602. We're going to put that one right in there. We have 1 HH bond. Okay, so we'd have to find HH. That's 436. We put that one right in there. We have 6 carbon hydrogen. Well, we already know that's 413. Man, that seems like a wasted step. I wonder if there's a way we could lazy that out. Preview of things to come. And then we have 1 carbon-carbon bond, and that's 346. So we plug that in right there. Okay. And now, typically on an exam, you'll probably even get this exact one right here. And this is just an easy chart for you to go ahead and use. Remember that you have to go down and find like the matching bond that it's with. Okay. Now the last part is to go ahead and do the maths. Okay. So you literally have to just do the math. Okay. So that means just double checking and making sure. Notice that the bonds that were formed, we made a nice little negative here. And altogether we should get negative 134 kilojoules per mole. Okay. Now notice this should mean that this takes energy to make this one. Or sorry, it doesn't take energy, but it releases energy when this compound is made. Okay, so this reaction ends up being exothermic. All right. And so that's the basic type and example for working through a problem like this. Okay, so I'm going to go ahead and start from here again. We label each type of bond, and then we indicate how many of each one there are. Then we go ahead and write in the energies for each type of bond. And then only after we've put in all the energies do we actually solve it out there. Okay. Now, lazy time. When we went ahead and did this, we had assumed that we broke apart everything. Okay. Now, if you've already got the Lewis structures, you might not have to do everything. Instead, you may be able to go ahead and cheat and only do the math for the bonds that are breaking and are not being remade on the other side. So as an example, we broke apart 4 CH bonds in our original thing, and we made 6 more. Okay, we don't actually have to do that math. Okay, the reason that we don't have to is because they're just going to be canceling out mathematically. Okay, so instead we could simplify our math by just seeing what changes are happening here. So here we are breaking apart a carbon-carbon bond. We are breaking apart the hydrogen-hydrogen. And we are making 2 CH bonds here. And we're reforming 1 carbon-carbon bond here. So that's going to be our actual difference, which means that we can go ahead and do that difference instead. And when we go through and do that process, what we'll end up doing is we'll still get the negative 134 kilojoules per mole. All right, and that's the lazy way for essentially solving problems like that one right there. Okay. I hope that this lecture helps you understand the bond enthalpy process. This is kind of a more complicated way of going about it. Obviously, if you have the enthalpy of formation available, that's an easier pathway because you could just subtract those enthalpies of formation. But alas, sometimes you do not have it available and you'll have to use a chart like that. If that is the case, I recommend that you draw out the Lewis structures just like we had for us before, and then just go ahead and use whichever changes are made in the actual compounds to help you figure out and examine what kinds of bonds are being broken and which ones are being reformed, and just going over like the core difference there. Okay. As always, I'm hoping that you guys are going to be able to find the laziest way to go through these, and hope it all makes sense and so that you're able to do this content well and easily. Until next time, stay lazy, my friends.